So, welcome back. We have just finished looking at the algorithms depth first search and breadth first search, and we observed that the basic difference between the two algorithms is the way in which they maintain the open list. In the case of depth first search, the new nodes that are generated by the move gen function, they are added at the head of the list, and therefore, we treat open as a stack. Whereas, in the case of breadth first search, the new nodes that are generated are added at the tail of the list, thereby treating that list as a queue essentially. In either case, we always pick the node for inspecting from the head of the queue. So, now we have a uniformity about this and we have a deterministic algorithm. Let us compare the two algorithms, the depth first search and breadth first search, in terms of their behavior. And what we mean by behavior is in what manner does the search algorithm explore the state space essentially. So, when you look at depth first search, for example, we know that it goes to the deepest nodes first. So, once it has generated the first set of children and it has picked one of them and generated its children, then it will pick one of the children of the first child, and then it will pick one of the children of this second child, and so on. So, it basically dives down into the search space till it hits a boundary. When it hits a boundary, it backtracks and then tries something else. So, here also we can see it is backtracking and trying something else, and so on. So, essentially this is the behavior of depth first search, and it is interesting to observe that the behavior is not influenced by the goal node at all essentially. It just happens the same every time you run depth first search on this particular domain. The behavior of breadth first search is also always the same, and that is why these two algorithms are called blind search algorithms or uninformed search algorithms, in the sense that they are not influenced by where the goal is essentially. Breadth first search as opposed to depth first search is a conservative algorithm. It tries to stay as close to the goal as possible. So, first it investigates the nodes which are closest to the goal, then it investigates the node in the next layer and then the next layer and the next layer, and in that manner it only goes away from the goal when it needs to, and as a direct consequence of this, it always guarantees the shortest path essentially. Let us look at an example with a tiny search space here. The move gen function is given in the table here. So, for example, S generates AVD and A generates CBS and so on. So, the importance of giving this move gen function is that we know in which order they will be generated, and therefore, we can decide which order they will be inspected in. The corresponding search space or state space is drawn on the left hand side, and we have marked S as the start node and G as the goal node. And this last column of the table also tells you that it is G which is the goal node, because for everybody else the goal test function returns false. So, our algorithm will terminate in two conditions: either the open list will become empty or it will find the goal node, and it will know that it is a goal node by applying goal test function to the node that it is looking at essentially. So, let us look at a few cases here. We have seen that we try to remove duplicates from open, in the sense that if you have generated some node, you do not generate it again, and when you say generated, you mean it is been put on open, and also if you have seen a node before, we do not add it again to open. So, in this first case where only new nodes are added to open, the behavior on this small problem of both depth first search and breadth first search is same. It will differ on larger problems, but we just want to understand the fact that how the space generated by the algorithm can vary from algorithm to algorithm. Now, in this particular case it so happens that both generate the same search space which is shown on the left hand side, but they will inspect the nodes in different order. So, if you look at depth first search for example, it will start both will start looking at 1 and they will generate the children of S which are given by the function a, b and d. Then that first search will look at this node 2 and then generate the child of 2 which is C. Now, we can see that there are 3 children of A, C, B and S. It has not added S because it is already on the closed, and it has not added B because it is already on the open. So, these two nodes are not added by this algorithm and only C is added as a child, and because that is the deepest node, depth first search goes and inspects this next, and after that once this is inspected, it has no more children to it does not generate any more children, because the children of C which are B and A are already been either added to open in the case of B or in close in the case of A. So, it has no further children. So, in some sense it goes back to open, and in open it has got B sitting there. So, it looks at the node B, and you can think of this behavior as going down to S and reaching a boundary, going down to C sorry and reaching a boundary, and then backtracking and going to B, then again reaching a boundary, then backtracking and going to D, and finally it will find a path to G. Breadth first search also starts off by looking at the node S. So, let us put this in square boxes just to distinguish from depth first search. So, this is for BFS and this one was for DFS. So, here also we generate the 3 children A, B, D of S, and here also breadth first search looks at the first child which is in the open, which is A, but it also generates C as a child of A like depth first search did, but it adds C to the end of the queue. So, as a consequence of this, the next node that this will see is B, and because B has no more children, the next node it will see is D, then it will see node C, and finally it will see node 6. So, you can see that the behavior of the two algorithms are different, but they are generated in this particular example the same state space. Now, this is the smallest search space you can generate, because you are pruning everything that you have either seen before or you have added to open before. So, let us look at some variations here. In case 2, we only look at nodes which are already enclosed and we do not add them again. The state space is still the same, but as you can see here, the spaces, the search spaces generated by the two algorithms are a little bit different. So, let us just follow the progress of these two algorithms, and we will put a double circle to stand for the fact that it has been put in closed. So, first of course, we inspect node S and generate its children A, B, D and put them in closed. Then we look at node A, and this is true in both the cases, depth first search and breadth first search, but here onwards the algorithm differs. When we generate the children of A, this time we have said that only if a node is on closed, we will not add it again. So, in this case S is on closed. So, of the 3 children of A which are S, B and C, we do not add S, but we add C and B. So, you will notice here that there are duplicate copies of B sitting here. We added this B because it is on open, but we have said that we will allow that to be added again, and even though both these instances of B are on open, we still add the third instance of B as open, and then when we put C on closed, and then we go to B and then we inspect B. Now, as you can see, you will end up inspecting B 3 times in this algorithm before you come to D and finally find a path to the goal node essentially. Let us look at breadth first search. As usual, it generates S as starts by looking at S, generates the 3 children A, B, D, looks at A, generates the children C and B. Again it has generated B again, because even though B is present in open, because our criteria is that only if it is on closed we will not add it again. But after looking at A, it looks at B and again adds C, and you can see that C is here and C is here as well. So, we have 2 copies of C. Then it goes and looks at D, and then it looks at this C, then B, then C, and finally at G essentially. But as you can see from this diagram, the search spaces generated by the 2 algorithms are different. So, let us look at the third case. In the third case, we do not, we just indiscriminately add everything that comes our way. So, whatever the moveGen function returns to us, we add that as the children of the given node, and consequently, as you can imagine, the search spaces generated are pretty large essentially. So, here we are saying that we will add all the nodes again and again. So, as you can see, for the case of depth first search, we at every stage we add the same nodes. For S we add A, B and D, because those are the 3 children of S. For A we add C, B and S. For C we add B and A, because these are the 2 children of C, and again for B we add C A S A C again, because these are the 3 children of B. But now you will notice that after having seen S and A and C and B, the algorithm is going to look at S again. Now, clearly you can see that it is in the same situation that it started, it has gone back to square one, so to speak, and in some sense it has gone back there. So, everything that it did from the start node S, it will repeat here, and consequently this algorithm goes into an infinite loop. It never stops coming out of this loop, and the loop that it is going through is from S to A to C to B, from S to A and A to C, C to B and B to S. So, this is a loop that it is constantly finding itself in. So, that is the danger with depth first search algorithm. If the search space is infinite, it can get caught into a loop. The search space for breadth first search also is infinite here, because we have put no constraints, we add all the children. But the difference is that in the tree that we see here, we start by looking at S, then because breadth first search goes down level by level, we look at A, we look at B, we look at D, then we go down to the next level. By the time we are finishing looking at A, B and D, we have generated its children C, B, S, S, A, C and G, and then when we look at C, we add these 2 children A, B, when we look at B, we add these 3 children A, B. So, we are doing the same thing, we are adding the nodes again and again and again without any constraint. So, we are, but the difference is that by the time we are finished with S, A and C, we can reach the goal and we can terminate here essentially. So, as you can see, even though the search space is infinite, breadth first search terminates, and not only it terminates with the shortest path. So, that is one plus point as we had observed about the breadth first search algorithm. So, in general, if you look at the behavior of depth first search and breadth first search, if you have a small search tree of depth 3 and branching factor 3 as well, then by the time you are looking at the 5th node. So, the order is given here, depth first search looks at the root first, then the left child, then the left child of the left child, then the left child of the left child of the left child, and then it reaches a dead end which is at level 3. So, in some sense it backtracks and goes and looks at this node next. So, the 5th node that it visits is this green node here, and the nodes that you see which are blank or uncolored, these are the nodes which are kept in the open. Breadth first search, as we have already said, goes down level by level. It looks at this node 1, then 2, then 3, then 4. By the time it has finished generating 2, 3 and 4, it has generated all the children of these 3 nodes, and as you can see, the size of open is large. In fact, we have observed that it is going to be exponential in nature. So, this again depicts the same thing that we were talking about, the different behavior of the 2 search algorithms as they go into a search space. The search space in this case is a small tree with branching factor 3 and depth 3. What about the running time of these two algorithms? Well, that really depends upon the location of the goal node. Now, if this diagram represents the search tree, and I try to draw search trees like this, trying to kind of hint towards the fact that they are growing exponentially, though of course, this is not really an exponential function, but anyway I hope it gives an idea. Now, if the goal node happens to be here, because depth first search dives into the search tree at some early point, it will find this goal and it will terminate much faster, whereas breadth first search would have gone down slowly level by level, eventually coming here and here and here and here, and then finding this goal node. So, if the goal node happens to be along the paths that depth first dives into, it will terminate faster. But if the goal node is, for example, on the right hand side as shown here, then depth first search will go down this and then backtrack and go down here, then backtrack and go down here, then backtrack and go down here, backtrack and go down here. So, it will take considerable amount of time by the time it finishes sweeping the search tree, whereas breadth first search would have gone down layer by layer and found the goal node faster essentially. So, it really depends upon where the goal node is in the search space. Now, let us talk about complexity of the two algorithms. We assume a constant branching factor b, and we assume for simplicity that the goal node occurs at depth z. So, this figure on the left shows that this is the search space generated and the goal node occurs at the last layer, and let us, for the sake of calculation, assume that it either occurs at the left end of this tree or at the right end of this tree. So, the time complexity is measured by the number of nodes inspected. Okay. And so, for depth first search we will call this number n DFS, for breadth first search we will call this number n BFS, and let us see what these numbers look like. If the goal happens to be in the extreme left, then depth first search will not need to backtrack at all, and in its first attempt itself, as it goes down this branch, it will find the thing after looking at d plus 1 nodes. So, d plus 1 because the root is the first node it inspects. Breadth first search on the other hand would have to completely search the tree up to the previous layer. So, it would have started like this. So, it has seen all these nodes, and you can verify that the number of nodes which is growing exponentially is given by this expression b raised to d minus 1 upon b minus 1 plus 1. When doing complexity analysis, we may tend to ignore these small constants which occur on the way. If the goal happens to be here, then both of them will end up inspecting the complete search space, search tree, and inspecting these many number of nodes, which is b raised to d plus 1 minus 1 divided by b minus 1. So, we want to see what is the average that they will see. So, we will assume that the average is the average of these two values. So, this value for depth first search and these two values which are given here and here, and you can see that after you ignore small constants, this comes to around b raised to d divided by 2. Likewise, for breadth first search, it is the average of these two values, the one on the left which we had written there, and the one on the right which is here, and this once you ignore those small constants, it comes to about this much. So, if you look at the ratio of these two values, that tells you what is the difference between the number of nodes seen by depth first search and breadth first search, and this ratio, as you can see from this here, turns out to be b plus 1 divided by b minus 1. There are two observations to be made here, that on the average time complexity is going to be exponential for either of these two algorithms, and the number of nodes inspected by breadth first search is only slightly more on the average than the number of nodes inspected by depth first search, and it is just b plus 1 divided by b minus 1. So, for example, if b were to be 9, then it would be 10 divided by 8 essentially, okay, which is about 25% more nodes that breadth first search has seen. And if branching factor is larger, this fraction will become closer to 1 essentially. What about the size of the open list? Because that is one criteria that we use for space complexity, and we will look at this algorithm, and as you can see, the open nodes are depicted by the blank nodes or the uncolored nodes, and the blue nodes are the closed nodes. And when that first search proceeds, it generates as it sweeps from left to right. You can see that the number of open nodes that it maintains is kind of not growing very rapidly. In fact, it is always a linear function with respect to depth, because in this small example, tiny example, we are adding 2 nodes at every layer essentially, and after we have finished adding seen some of them, it becomes less than 2. So, at every layer we are adding b minus 1 nodes, where b is the branching factor, and therefore, it, as you can imagine it, the search space grows linearly. Breadth first search on the other hand finishes looking at a layer, generating all its children, and then when it goes to the next layer, it has generated all its children. So, you can see that the size of open is growing quite rapidly, and in fact, you are multiplying. If you use this as a symbol for multiplying, then you are multiplying by b as you go down essentially. In the case of that first search, you were adding a constant amount as you went down, and therefore, the search space was growing linearly. In the case of breadth first search, you are multiplying by a constant amount, and therefore, it is growing exponentially. Okay, so, this is how the search frontiers of the tool look. The pink nodes that you see here is the search frontier for the depth first search, and this yellow nodes that you see here is the search frontier for the breadth first search. And as you can see, the pink nodes are growing linearly, you are adding a constant number at every level, and the yellow nodes are growing exponentially. As the depth first search algorithm sweeps from left to right, the number of open nodes keep decreasing, because it has seen all of them essentially. So, if you look at these two properties of the two algorithms, then you can see that for both of them time complexity is exponential in nature. If you look at space complexity, which is the size of open, time complexity can be thought of as the size of closed, because those are the nodes that you have seen, and space complexity is the set of candidates that you are keeping, which is the size of open. And you can see here that depth first search wins on space complexity, but breadth first search wins on the quality of the solution, because we have already observed that it will give you the shortest path. In terms of completeness, for finite search spaces, both are complete, in the sense both will end up exploring the entire space. But if you have infinite search space, we have seen that depth first search can go into an infinite loop essentially. Whereas, again this is a plus point for breadth first search, that it is guaranteed to terminate if there is a path to the goal node, because the path will always be of a finite length, and breadth first search goes down level by layer, exploring paths of greater length. So, can we have an algorithm that uses linear space for open and which guarantees the shortest path? Okay.